Greetings to everyone and welcome to the 2021 McDonald Distinguished Lecture. I'm Brad Jolliffe, Director of the McDonald Center for the Space Sciences here at Washington University, and it's my great pleasure to welcome you all to this public lecture. Students, faculty, colleagues, alumni, friends, and special guests. We have Chancellor Andrew Martin with us today and very special guest, Mr. John McDonnell. We are most fortunate here at Washington University to have the McDonald Center for the Space Sciences, which was made possible by a very generous gift from the McDonnell Aerospace Foundation and later supplemented by a gift from the Danforth Foundation. Perhaps our main event during the year, once in the spring and once in the fall, is to host a public lecture by a distinguished scientist on an issue of great interest and importance in space science. And this evening, we're honored to have Professor Katherine Freese, the Jeff and Gail Kodosky Endowed Chair in Physics from the University of Texas at Austin, delivering the distinguished lecture on the dark side of the universe. And if you have seen her book, The Cosmic Cocktail, you know that it's about dark matter. Under ordinary circumstances, she would be here in person, but she's graciously agreed to do this remotely, given current restrictions on travel and gathering. So Zoom it is, and we're just delighted that you are all joining us. So now I'd like to ask Professor Mark Alford, Chair of the Department of Physics here at Washington University, to introduce our distinguished lecturer. Mark?
Thank you very much, Brad. Yes, I'm the Chair of the Physics Department here, and it's a very great pleasure to me to welcome Professor Katherine Freese. She's been known to us for many years as a major figure in cosmology, particularly in dark matter and inflationary theories. She was an early proposer of ways to do indirect detection of dark matter and a leader in the quest for natural models of inflation in the early universe. And I just want to give you a little bit of sort of historical background. Katherine was one of the first women to get a BA in physics at Princeton. She then did her PhD at Chicago with David Schramm and held postdoctoral positions at Harvard and the Institute for Theoretical Physics in Santa Barbara, which then became the Kavli Institute, and at UC Berkeley. And she was an assistant professor at MIT and then a professor at University of Michigan. And along the way, she's played important leadership roles. She was the associate director of the Michigan Center for Theoretical Physics. And at the international level, she was the director of Nordita, the Nordic Institute for Theoretical Physics based in Stockholm. And as you've just heard, she's the author of a popular book on cosmology, The Cosmic Cocktail. And she's basically going to be telling us the ingredients for the cosmic cocktail very soon. So since 2019, she's been at UT Austin as the Jeff and Gail Kodosky Professor of Physics. That same year, she was awarded the American Physical Society's Julius Edgar Lilienfeld Prize. And I'm just going to read a couple of sentences from the citation for that. For groundbreaking research at the interface of cosmology and particle physics and her tireless efforts to communicate the excitement of physics to the general public. And then just last year, she was elected to the National Academy of Sciences. So we are honored and delighted to welcome Professor Katherine Freese as the 2021 McDonald Distinguished Lecturer.
Mark, thank you for that lovely introduction. And I also have to say thank you. You have been a colleague and friend for decades, as have others in your department. So this is really great for me to be giving this public lecture today. So I will now, I cannot share my screen because somebody else is sharing screen. Here we go, now I can. So let's get this going. And what I want to do is get it into full screen mode and.
Katherine, that's in the presenter mode, if you want to flip it.
Oh, I have to start over, okay? Let me. Got it, right? This works.
There it is. Thank you. Good.
Okay, great. Well, before starting my lecture, on my subject, I want to reflect back on humans throughout history, since antiquity, asking big questions about the universe. Who are we? Where are we going? What is the universe made of? What's out there? And they had creation myths. And the amazing thing is that since the work of Albert Einstein in 1915, we too have a creation myth. It's called the hot Big Bang, but the difference is it's not a myth, it's reality. So if you think about the progress in human history in terms of modern cosmology over the past 100 years, it's really mind-boggling and fascinating. So soon after Einstein wrote down the theory of general relativity, others applied the equations to the universe as a whole and realized that several possible solutions to the equations existed, meaning that the universe could be expanding or contracting or static. And Einstein was really in favor of the static universe because it's a very symmetric situation. He liked that idea. And well, so sometimes your theoretical preference has to give way to reality, and that's what happened. So in 1929, not much later, Edwin Hubble figured out the answer to this evolution of the universe, and he was using the Mount Wilson Observatory above Pasadena and made some astonishing discoveries. One of them is, well, if it's quite remarkable, at the time of Einstein's theoretical advances, observational astronomy was at that point really quite primitive. People didn't even know that there's anything out there beyond our galaxy. They thought all the stars that we see, that everything out there is part of the Milky Way. Then there started being speculation, well, maybe there are island universes. And it was Hubble who made the major contribution showing that, well, some things just have to be so far away that there have to be galaxies beyond our own. Then in addition to that, he looked at light from those galaxies, and he looked at them at various distances away from us and realized that the light that's coming to us from those galaxies had to be stretched or redshifted by the time it got to us. So there were atomic emissions, and you know exactly what the wavelength of that emission is. And so I've plotted it here. Let's say you're blowing up a balloon. And so these are the atomic emissions of the light from these galaxies. And then as this balloon blows up, well, the wavelength gets longer. So by the time he saw the light, the wavelength had been stretched. And the conclusion is that the universe is expanding. So this was really a major contribution to our understanding of the universe, and it forced Einstein to abandon the idea of a static universe. So we live in a universe in which all the galaxies are on the whole are moving apart from all of the rest of them. Now, I have to say, of course, if there's two things that are really close together, that's not true. So for example, we are swallowing up other mini smaller galaxies. The Milky Way is eating the Sagittarius dwarf galaxy, and so on and so forth. So if you're close enough together, gravity wins. But on the largest scales, the universe is expanding, and that is what is making these things move apart from one another. So the idea of the Big Bang in cosmology is that the universe started out very, very hot and very, very dense 14 billion years ago. So you can think of it as a primordial soup of particles, of quarks and leptons and photons and other particles. And at first, these were very, very tightly packed, interacting with one another constantly and very, very hot. But then as time goes on, these particles spread apart, and the universe, although starting out really hot, has been cooling and expanding ever since. There's kind of a fun model of this, the raisin bread model of the universe. So you can think of the raisins in this loaf of raisin bread as being models for the galaxies. And if you now take this dough and you put it in the oven, they tell me the dough rises, and I still have yet to meet anybody who's actually made raisin bread in an oven, but I'm sure you're out there in this audience today. So when you do that, you know that this bread, the dough rises, which means the raisins move apart from one another, not because they're doing anything, they're not running away from each other, but simply because they're embedded inside the bread itself. So that's kind of a nice analogy for what's going on in the universe. But there's a very big difference between the raisin bread and the universe, which is that the raisin bread has a central point, whereas we believe that the universe does not. There's no special point in the universe, which means if I go back to this picture, let's move to some other galaxy, not our galaxy, but a different one. So wherever you are, you would see other things moving away from you. Okay, so now let's talk about the notion of the Big Bang. So as we go backwards in time, what happens? Well, things contract and they get closer and closer together. And so certainly it is true that everything in this room will contract to a point. But what about things that are out at infinity? Is this possible the universe is infinite? So when you contract things closer and closer together, you still would have something out at infinity. So eventually, when you contract things tighter and tighter together, it's not that they're contracting to a point. Instead, what happens is they get so densely packed that we lose our physical description of what's going on. If you want to go any farther back in time or to higher density, then you would need to have a theory of quantum mechanics together with gravity. In other words, a theory of quantum gravity, but we don't have that. String theory is our best bet at the moment, and people are trying to work out how you could go backwards before the Big Bang, in other words, beyond this density. So the Big Bang is not a point in the universe, it's really a point in time. So it's not an explosion either, but if you'd like to have one, then please put one everywhere in this infinite universe. So where do we stand in cosmology? Well, I mentioned that in the past 100 years, it's just mind-boggling how far we've gotten. And the progress has accelerated. So some of the big questions have been answered even now at the turn of the millennium. We know what is the geometry of the universe, the total mass and energy content of the universe, the age of the universe, the basic idea for the formation of structure. These are all things we know, but there are plenty of big questions unanswered. And today, the one I want to talk about is, what is the universe made of? What is the dark matter? What is the dark energy? So getting back to some of the progress we have made, it was clear in the 1930s that there were three possible geometries for the universe, which would lead to three possible evolutions. One is that we would be living on the surface of a sphere, and I don't mean a normal sphere, I mean a higher dimensional sphere. Or it could have been a saddle shape, or the universe could have a flat geometry. And again, this is not meant that the universe is two-dimensional. It means that the geometry is flat so that a triangle looks really normal. The angles add up as usual to 180 degrees. Whereas in these other geometries, these angles do not add, in one case, they add up to more than 180 degrees, in the other case to less than that. So of these three possible geometries that were postulated in the 1930s, we now know the answer. The geometry is flat. So showing a little bit more about this. So let's say we have this little guy here who is sitting on top of these, he lives in these three possible geometries. And so in the flat geometry, then parallel lines would never meet. If you shoot out two laser beams, they're not going to meet if they're in absolutely parallel lines. Whereas in these other two situations, either they diverge, or if the universe were the surface of a sphere, then these laser beams would, well, the universe is bigger than this, but they could in principle come back and bite you from behind. Well, we know the answer to the geometry of the universe from the cosmic microwave background light, which is left over from the hot early epoch of the universe. So this is light that was produced when the universe was about 400,000 years old. And let me remind you again, that's nothing in the grand scheme of things, because we're now at 14 billion years. And the trick is that if you look at the hot spots and cold spots in this light, in the cosmic microwave background light, some regions, which are shown in orange, are a little bit hotter, whereas the regions shown in blue are a little bit colder than the average. And I'm talking 1 part in 10 to the 5. So there's a very, very small anisotropies. But it's the size of these regions that tells you the geometry of the universe. So what was predicted that if light moves in a straight line to us from this time way back in the universe, then these hotspots should be about 1 angular degree in size. Whereas if light was moved in a curved path, then it would be different than 1 degree. It could be larger or smaller, depending on if it's a sphere or a saddle. So sure enough, here we go. At 1 degree angular scale, there it is, sticking up the Doppler peak. Indeed, the geometry of the universe is flat. The size of these hot and cold spots is 1 degree in scale. And notice these other peaks in here, because they're useful to tell us an enormous amount about cosmology, in addition to what the geometry is. So this happened at around the turn of the millennium. And what I mean by flat geometry, I want to be sure and be clear about this. As I said, it's not a two-dimensional universe. Instead, let's take a cube, and let's take each of these sides out to infinity. And what I mean by flat geometry is that there's no curvature. It's just a cube where the shortest distance between 2 points is a straight line, no curvature, no weird geometry. That's all that I mean. So now that we've got the geometry of the universe, we can use Einstein's relativity equations. And I promise this is the only equation in my entire talk. And so what Einstein's relativity does is connect the curvature of space with the matter and energy content. And these are a bunch of constants out front. So once you know the geometry on the left-hand side, that tells you the total mass and energy on the right-hand side. And an example of this, you've probably all seen pictures like this, is that the mass warps the geometry. So here you've got the Earth and it warps the geometry around it because mass and space-time are related. So a flat geometry corresponds to an energy density of 10 to the minus 29 gram per cubic centimeter. So that's the average energy density in the universe. And let's compare that to water on Earth, which has 1 gram per cubic centimeter. So as I tried to explain to the Queen of Sweden, it was a funny story. This is, I guess, what you would say, this is outer space. This is the density of outer space. So from this cosmic microwave background light, this also leads me to tell a joke. So this is from an earlier NASA satellite that has the same data. And there we go. The initials of Stephen Hawking are in there. And those are, I guess those are cool spots in the light. Okay, so let me turn now to the topic of today's talk, which is, what is the universe made of? And here we have a very, very surprising answer. If we take everything in our daily experience, we take our bodies, we take the chairs we sit in, the cocktails, the earth, the sun, everything that we know about, the air we breathe, all of this is made of atomic material. But all that atomic material only adds up to 5% of the total content of the universe. What a bizarre situation. Here we have ordinary matter and the air that we breathe, all the ordinary stuff, only making up 5% in this pie picture of the universe, leaving about 25% dark matter and about 70% dark energy. So this is indeed the dark side of the universe that I'm talking about today. And it leaves us with wondering, oh boy, what are these things? We have to figure this out. So the dark matter problem actually is now, I meant to change this number. This is a 90-year-old problem. It dates back to the 1930s. So Knut Lundmark in Sweden, and famously Fritz Zwicky, a Swiss scientist working in the same telescopes as Edwin Hubble. Zwicky in particular studied the coma cluster of galaxies, which contains hundreds of galaxies. And he noticed that the ones on the outskirts were moving really, really rapidly. But normally the speed of those things should be determined by the stellar light of the galaxy's interior to those orbits. And the math didn't work out. There had to be something else in there, some additional material that is speeding up those orbits. So the proposal was that it's dunkle Materie, the German for dark matter, could provide the explanation. And the word dark in here is very, very simply means it's not bright stars, it doesn't shine. It's not something you can see with telescopes. So after that, there was a lot of question as to whether this dark matter problem was real or not. And it was really finalized by the work of Vera Rubin and Kent Ford in the 1970s, who looked at galaxies and they discovered that every single galaxy has dark matter in there. And that's when the scientific consensus became that, well, dark matter really exists and it's in every one of these large structures and we have to go understand it. So the kind of work that she did, she used rotation curves, and she used rotation curves of galaxies, but let me now go away from dark matter entirely and just use it as an analogy, the solar system. So let's look at the average speeds of the planets. Okay, we'll start out, 0 is the sun. And then as we move to the right, we're moving to farther and farther away from the sun. And here I'm plotting the speeds of the planets. And so the first one is the fastest, that's Mercury. The second one, Venus, is the second fastest. Then it's Earth, Mars, and you'll notice a pattern that the speed drops as you move out. And I was supposed to remove Pluto, but accidentally I added a 10th planet. I thought, well, that's fun, let's just leave it. So in fact, the equation that we expect to follow, I lied, there is another equation. So The speeds are determined by the mass of the sun and the distance away from the sun. So as the distance goes up, these speeds go down. So that all makes sense in terms of the solar system. And you also notice, let's say the sun were 4 times as massive. Well, then everything would be moving twice as fast. So again, this slide has nothing to do with dark matter, but it provides a useful analogy. And before I leave the solar system, though, I do want to tell you about Tycho Brahe, who was one of the people who made the measurements of these planetary orbits in the 16th century. So he was quite a character. He lost his nose in a duel and then ever after wore a gold and silver replacement. I can't resist telling the story that I'd always heard that he died of a burst bladder at a dinner with the king. But then about 10 years ago, there was a competing theory that they decided to test, which is that his student, Johannes Kepler, had poisoned him with mercury poisoning. And the famous Kepler's laws should really be Brahe's laws. So they actually dug up his body in Copenhagen and did analysis of his mustache hairs and discovered there was no mercury poisoning. So I guess the story of the burst bladder is actually true. And let me tell you, when I was at the Nobel dinner, and you're in your ball gown and and I did get up to go to the bathroom, and I was reprimanded because you're not supposed to get up until the king does. So I believe now, I really do believe this story. He wasn't allowed to get up, and well, in the modern century, to heck with it, I just did. But anyway, okay, so I'm getting carried away with stories, but let's get back to dark matter. Now let's switch from the solar system to galaxies, where you also have similar kinds of rotation curves. So as we move in, this is the center of some galaxy, and we move out a distance r away from the center, and we look at the orbits of things around the center of the galaxy. So the same thing is true here, that the more mass you have in here, inside the middle, inside the orbit, interior to it, the faster that this stuff is going to move. So what Vera Rubin did was look at how fast things are moving and realize, well, based on the stellar material interior to this orbit, it doesn't make sense. We better add some more matter, and that would be the dark matter. So here's a picture of the rotation curves similar to the ones. This one's actually not from Rubin, but it's very similar. And so this is what you'd expect, something like the solar system. The speeds should drop off as you move out. Yeah, well, that's not what they saw. They saw this flat rotation curve instead. And so they decided, okay, we have to add in more matter. So if we add in this additional dark matter, then we can explain these flat rotation curves. So our galaxy is a perfect example. So our Milky Way, at the center, there is a supermassive black hole. And this is pretty cool because it is the origin of the 2020 Nobel Prize in Physics, at least, well, half of it was for the discovery of this supermassive black hole. It went to Andrea Getz and Reinhard Genzel, and this thing weighs 4 million times as much as the sun. And it's shown in yellow just so you can see it. So there's this supermassive black hole at the center. Then there's this pinwheel of structure of spiral arms, and that's where all the stars are in our galaxy, including the sun. So now let's take this pinwheel and put it on the side, and we call this the disk of the galaxy. Then as you look out here, you see, for example, here's the sun, which is 25,000 light years away from the center. But that disk is just a tiny piece of the whole thing. And in fact, if we look at the galaxy as a whole, here's the spiral structure, but there's this giant thing here made of dark matter. And we call this a dark matter halo. So I always want to warn people, supermassive black holes are not the dark matter. Every galaxy has one at the center, but they only make up a tiny fraction of the universe as a whole. So they don't add up to explain the dark matter. So it's important to make that distinction. Okay, so the first evidence for dark matter was from these rotation curves. And since then, it's like a jigsaw puzzle, many, many pieces, and they all add up to the same thing. We know dark matter has to exist. So another way to find it is, again, it came from an idea of Einstein's, which is gravitational lensing. So whatever mass you have, in this case, it's a massive compact halo object, it doesn't matter. Any mass bends light. So this dark matter doesn't give off light, but it does bend the light that comes from behind it. And so a star's light would be bent on the way to your telescope. And if you didn't know better, you'd think, oh, well, okay, so there's a star here. But then you might notice, but there's another image. There's multiple images of the same star. and the images are sheared and strange looking. So by studying the background light, you can learn about what the distribution of dark matter is in between the light and you. And there's an app that you can get on iPhones that was created by a Michigan student that actually has the correct gravitational lensing equations in it, and you can lens yourself more and more and more, which these students did. So now let's look at Hubble Space Telescope at some actual lensing by dark matter. And so you have, this is quite a complicated picture, and I don't know all the details, but you can certainly see in here these sheared multiple images of background galaxies, which teaches you about the dark matter on the way between the galaxies and us. And now you can do a computer reconstruction of the dark matter that's in the way. So this is also Hubble Space Telescope data that has been reconstructed. It's not the same image, but we've used a computer to reconstruct where the mass is in between the light and us. And so you see this is a cluster with all these peaks or the galaxies in the cluster. And then there's additional dark matter in between the galaxies as well. So the clusters have lots of dark matter in them. Now, there's another piece of evidence for the existence of dark matter, and that's the bullet cluster. What this object is there are two clusters that have collided with one another. And when they did that, part of the matter got stuck and part of the matter did not. So the gas has electromagnetic interactions, it has strong interactions, which is what holds your nuclei together. And so the gas, when it collides with other gas, gets stuck and gives off X-rays. And so it's sitting there shown in pink. It's as though you and I collided, and of course we'd get stuck. We wouldn't get very far. But there's this other stuff seen also by lensing this, which it's just shown in blue. And there's another component of matter that behaves completely differently, and it just kept going. It didn't get stuck. So it doesn't have the same interactions that made the gas get stuck. So here's a clear evidence that there's really two different types of matter. Then one more thing that's kind of interesting is to point out that without dark matter, we would not be able to exist because ordinary matter doesn't clump quickly enough. It talks to photons and these things stream out of structure. You can't make galaxies quickly enough with ordinary matter, but the dark matter can do it for you. It can form the structures, and then later on, the ordinary matter falls into those structures. And this is a computer simulation that shows how that works. So we start very early in the universe with the dark matter particles shown in blue. And this particular computer simulation only has dark matter in it. But then if these particles are almost uniformly spread out, but not quite, and what happens as time goes on is gravity makes them clump together. And as time goes on, they clump together more and more and more until you reach the final stage, which is a very good match to our universe today. So you can see these filaments of dark matter. And again, the light stuff, the stuff that's shown in blue is actually the dark matter. And where the intersections of the filaments, that is where the galaxies are. So I've talked about a number of pieces of evidence for dark matter, including gravitational lensing and the rotation curves. There's some things I didn't mention. One of the most important is actually, I did say that in this cosmic microwave background light, not only do we learn the geometry of the universe, but from the other peaks, we also learn the amount of dark matter. So that's a very important piece of evidence as well. All right, so I've argued that this stuff has to exist. So now let's ask, yeah, but what is it? So in the early days, people tried simple things like gas, rocks, dust, stuff like that. And well, that got ruled out pretty quickly. And let me go back on that slide for one more minute. I worked on one aspect of this, which is we tried to see, could it be faint stars or planetary objects or stellar remnants? And we showed that this doesn't work either through a combination of theory and observations. And then there were also microlensing experiments that showed the same thing. So ordinary stuff doesn't do it, and we're driven to exotica. We have to look at very unusual new things that have been proposed. And I will come back to these two in a minute, which are the most strongly motivated of all the candidates. But I just wanted to mention, look at this. There are so many ideas that people have, and people are, and there's active research going on many of these. So neutrinos would have been great. That would have been the easiest because neutrinos definitely exist. but they don't work very well because it turns out they're just too light. So they were there is was discovered their mass is about their mass is about they add up to about 0.5% of the galaxy, which is just not enough to solve the dark matter problem. And not only that, because they're so light, they also ruin galaxy formation. They move out of galaxies instead of making galaxies clump. Then another interesting candidate is primordial black holes. So these are not the supermassive black holes. What they are instead is very early in the history of the universe, you could make, there's phase transitions or other unusual things going on where you could make primordial black holes of a variety of different masses. And I like to always show pictures of people in my group, and he was my former postdoc who's written a very nice review that you can look at about primordial black holes. So these are all very interesting candidates, but the two that are the most highly motivated are axions and WIMPs. And so I wanted to talk about those two in particular. And the reason they're highly motivated is that they exist in particle physics for reasons that have nothing to do with dark matter. So in work that people are doing in theoretical physics, these objects are byproducts. They're there anyhow. So it's like killing two birds with one stone. No, they haven't been, none of these have been discovered, but the motivation for them is good. And so axions, for example, they're very light particles. The proton they're a trillionth as light as a proton or more, or even lighter. But they're in the theory of strong interactions, which is what holds your nuclei together. There were some problems with that theory, and the solution to that problem automatically predicts axions. So I'm not going to talk too much about them. I just want to mention again, this is a former postdoc of mine, Luca Visinelli, who's written a review on the search for these particles. And I have to mention it because it's a very active area of people looking for axions or axion-like particles, which exist in string theory. So the theory is this yellow line here, and then here are all the experiments going after this to try to figure out what these particles are, whether or not they're there. They're trying to discover them. But that's not what I'm going to focus on. I'm going to move now to the other. Let me go back again to this slide. Yeesh, I seem to be going forward instead of backwards. Oops, my apologies. So back on this slide, I mentioned that these are the two most strongly motivated. And so I mentioned briefly the axions, and now I'm going to talk about the WIMPs. So what these are, WIMP stands for weakly interacting massive particle. And billions of these would be passing through your body every second. And one a day or one a month hits you, but it doesn't do any damage. And that's because, as I've said before, it doesn't have strong nuclear forces or electromagnetic forces. But the interesting thing is there are 4 forces of nature that we know about. And so other than those 2 in gravity, the remaining one is called the weak interaction, which is responsible for some types of radioactivity. So the way that these guys became interesting is that people said, yeah, well, okay, what if there is some particle out there that feels the weak force? What would its properties be? What would happen? And by the way, these things weigh about 1 to 10,000 times as much as protons. So there's 2 reasons that we think WIMPs are particularly interesting. And the first one is that if the only ingredient is that it's a weakly interacting particle, the same weak interactions that give you radioactivity, then you automatically get the right numbers of WIMPs today. So in the early universe, we know how to calculate things. We know how to figure out how many particles there are. And so you can, the WIMPs annihilate, they're their own antimatter. They're unusual. And so they annihilate among themselves. And you can ask how many are left today. And if the annihilation rate is set by the weak interaction, then you get the right answer for the abundance of WIMPs today. So this is called the WIMP miracle. You assume the weak force determines how many particles there are, and you get the right abundance by chance or by a miracle. The other reason that we like WIMPs is because they're already there in theories that people have proposed as extensions of the standard model of particle physics, such as supersymmetry. And here, for every particle, we know there's a partner. Most of these are heavy and they decay to lighter and lighter ones until you get to the lightest supersymmetric particle. And that thing is a WIMP candidate. So that's a particle that's automatically sitting there in theories proposed for other reasons. So let's say if we want to take this WIMP idea seriously, then we have to go search for them. And if we read from left to right in these pictures, then there's multiple ways to look for these particles. And I wanted to briefly mention how to do that. So one of them, this is the CERN particle accelerator outside of Geneva. Though yes, you can ski in those mountains. So the Large Hadron Collider shoots protons in opposing directions, moving at nearly the speed of light. And those protons collide in the detectors that you can see are ATLAS and CMS. And then we look what comes out when those two protons collide. I have to show some pictures of people that are playing an important role in these experiments. So Fabiola Gianotti, she is now the Director General at CERN. And this is, I mentioned the ATLAS detector. Look how giant this thing is. Some guy just standing there in front of it. These are really amazing. Some people call them the cathedrals of the modern era. I mean, this amazing developments. And here's Peter Higgs. You may have heard about the Higgs boson. So this collider did discover the Higgs weighing about 125 times as much as a proton. So the Higgs was discovered. And the next major goal is to look for supersymmetry, to look for dark matter. The way this would work is that when protons collide, you would get a chain of supersymmetric particles, and in the end, the dark matter particle would escape the detector. So at this point, there's no discovery of these things yet, and so that means particle masses are being pushed higher, but these searches are ongoing at the Large Hadron Collider. Now, other ways to look for these things is take advantage of the fact that you've got so many of these particles inside the halo of our galaxy, including going through us and potentially going through our detectors. And when they hit a detector, then they scatter off, they bounce off and heat up the nucleus just a little bit. So you can look for that energy deposit, very, very low count rates, 1 count per kilogram per day. And this leads me to how did I get into dark matter? Well, as a PhD student at Chicago, David Schramm was one of the leaders, one of the founders of the whole field of this astroparticle physics. And so I have to always advise students, find a great mentor. I sure did. And then I went as a postdoctoral fellow to the Harvard Center for Astrophysics, where I met this guy, Andre Drukier, and he had been looking at scattering at weak interactions of neutrinos. And then we were among the first to write papers on, well, yes, if neutrinos can do it, then so can WIMPs. And so we studied this scattering picture that I showed you. So we studied this and we asked, okay, what would it take to find these things? And so as a consequence, we made predictions for what you could look for, and people started building WIMP detectors, and they have to be in underground laboratories to get away from competing cosmic rays that are flying around in the galaxy. So this is one of these experiments in the Gran Sasso Tunnel underneath these mountains outside of Rome. At this point, it's a worldwide effort with these underground dark matter experiments. And there's only one of them, this Dama Libra experiment in that same tunnel that I just showed you, that does see something. And what they see is something we predicted, which we predicted that as the Earth goes around the sun, you would have a count rate of WIMPs in the detector that would go up and down with the time of year. This is what we predicted. And their data is in red and blue. And sure enough, they are definitely seeing this annual modulation. They have a peak of count rate in June, a minimum in December, and they've got 13 years of data. But we don't know what to make of it because the experimenters have not released their data to the public, which would really help. And then we also don't know what to make of it because other experiments are not confirming their results. They see no signal. And then we have these fun personalities. We have Juan Collier leading the one experiment saying, I'm a Spaniard caught between 2 Italian women. This is women leading some of these other experiments. So right now, it's really hard to know how to compare the experiments, though, because the Dama experiment that has a signal is made of sodium iodide crystals. But the other things that don't have a signal are made of xenon and other elements. And once you postulate exactly how the scattering happens, you could I'm going ahead to my fun pictures, but anyway, so the question is, these green regions from the Dama signal that is positive, are they ruled out by the red and green regions where you need to be below these lines because nothing's seen? But the answer is, well, no, not really. To plot them on the same plot, I had to make assumptions that I don't know if they're right or not. So the problem is, because these things are made of different materials, it's very hard to put them on the same plot. So in the meantime, we have a lot of fun. This is at the every other year, the UCLA Dark Matter meeting. And here is Rick Gaitskell of the LUX experiment, which is in the previous picture, one of those lines you had to be below. But so what has to happen is this perplexing situation where only this one experiment sees something, you have to, and that's after 13 years of data, there are now 3 other groups using the same material, namely crystals also made of sodium and iodine. And so there's these 3 experiments that are taking data, and they have tentative results already, and tentatively already in tension. So I wish these slides would just stop jumping. I don't know how to make them stop. So the DAMA data are these blue squares, but this unease experiment, well, it's still compatible. It has to be somewhere in this region. But so the moral of the story is, in the next few years, we'll know if DAMA's right or not, because these other experiments are testing it right now. Well, that leads me to some new ideas that we have for dark matter detection that I really have to tell you about. And one of them is the idea of using DNA. So what I've got in this picture here is a nanometer thin plate of gold. It just is 1 atom thin with DNA strands attached. And you can buy this from a company called Illumina. They make it. It's not good enough for the dark matter experiments, but the technology for attaching DNA to things, including gold, is there. So what happens is, when the WIMP comes along, although it's not going to break the DNA, it knocks a gold nucleus out of this plane, and then the DNA, the gold goes through the DNA, and the gold breaks the DNA. And then you can figure out, because the techniques in biology are so advanced, you can figure out exactly where this break happened. So you can figure out the track of the gold, which means you can go back and reconstruct the track of the WIMP. And if you really know where the WIMP is coming from like that, that's going to help a lot as far as making sure that you understand what's going on in your experiment. So there's another way to search for the WIMPs. I've talked about producing them at the LHC, scattering them off of nuclei, and the third type is called indirect detection, and that's where you take WIMPs, because they are their own antimatter, they annihilate among themselves, and they go through a chain of particles, and in the end, what you get is neutrinos, positrons, and gamma rays. Gamma rays are high energy photons. And the interesting thing is that there are experiments looking for all 3 of these things, but the one that has the most interesting situation is actually the Fermi satellite, which is a detector of high energy photons, high energy light, called gamma rays. And they look towards the center of the galaxy, and it's possible that right at the center of the galaxy, there is an excess, and that could be, oops, sorry, jumping again. There's an excess at the center here that could be gamma rays that are due to the annihilation of dark matter. So there's a lot of discussion about what has been seen there. So putting together these pieces, there is possible evidence for WIMP detection already now, including this DAMA annual modulation, but you have to understand the details of the theory, the particle theory, the nuclear physics, everything that's going on to understand why other experiments are not seeing it. And then indirect detection, there is this excess of gamma rays from the galactic center so these are the possible signals. And then theorists are looking for models where all of this might be all of these different experiments could be consistent. And we're waiting for these other experiments made of the sodium iodide crystals. Well, I do have to take some time to talk about a 4th way to search for WIMPs, because this is my baby. These are dark stars. And so the idea is that the very first stars that form in the history of the universe, they'd be really different from stars now. Nowadays, the sun is powered by fusion. You have 4 helium atoms combining to make helium in the core of the sun. And the whole process requires a really hot central temperature for the sun. But it's possible that instead you would have a different power source for sun, and that would be dark matter annihilation. And this is an idea that that we came up with, Douglas Spoliar, Paulo Gondola, and I. And yes, this movie predated our idea. But the basic idea that we had was, now we're working with many other collaborators as well. The basic idea that we had works something like this. So when the universe is a few 100 million years old, all of a sudden you get a collapsing cloud of molecular hydrogen at the centers of dark matter halos. So these are precursors to stars. So on the way to making protostars, these collapsing clouds of hydrogen, they're smack in the middle of these proto-galaxies where there's a lot of dark matter. And then dark matter annihilation can set in and become really important. And the dark matter annihilation products get stuck inside this collapsing cloud of hydrogen, and they produce a very unusual kind of star. So I want to emphasize that these dark stars are made almost entirely of hydrogen and helium. I wish they would stop jumping. Okay, so, and the dark matter constitutes less than 0.1% of the mass of the star. So no, dark stars are not made of dark matter. They're ordinary matter, and they're powered by dark matter. So, and in fact, they start out about the size of the sun, but because they're very strange looking. They're actually, the radius of these things is about 10 times the distance between the Earth and the sun. So they're big, giant, puffy objects, and yet they're really, really cool. The temperature is not there to create fusion. It's not there to prevent stuff from falling onto them. So they start out the size of the sun, but they can grow to 1 million times the mass of the sun, and 1 billion times as bright as the sun, which means, if that's true, then the supermassive dark stars are detectable. So the Hubble Space Telescope has a sequel that's going to launch in 2023 called the James Webb Space Telescope, and that thing would be able to discover these supermassive dark stars. So I'm very excited to look forward to that. Another thing that's fun about dark stars is, well, once the dark matter power runs out, then what happens? Well, if you've got if you've got a dark star that is 1 million times as massive as the sun, it will collapse to a black hole, a giant black hole. And this could be the origin of supermassive black holes that are seen throughout the universe, and not as just at the centers of galaxies, but also in the early universe. So I have talked about different ways to look for WIMPs: direct and indirect detection, the collider searches, and looking for dark stars. So I wanted to end with mention just a few words about dark energy. So the reality is, we know dark matter exists, and we understand at least the fact that it's matter. And the definition of matter is that it feels gravitational attraction. It forms galaxies and clusters and so on. So we know a lot about its behavior, even if we don't know the particle that it's made of. But dark energy was a huge surprise when that also was discovered at the turn of the millennium, because this stuff does not feel gravitational attraction. In fact, it's causing the universe to accelerate. And we might as well call it, I don't know, gobbledygook. We really don't know what it is. So both on the theory and the observational side, it's a really tough problem. So on the theory side, the best bet is that it's some kind of vacuum energy that would be particles popping into and out of existence, but we don't really know. What we do know is it has a repulsive type of behavior. It's causing galaxies not just to expand, but to accelerate apart from one another. And so this is a huge conundrum to figure out what this stuff is. So I'm going to end with a joke, which is the three of us at the World Science Festival in New York. The three of us were talking about dark matter on this panel, and these three guys were talking about dark energy. And I made the one statement, the only thing we actually really know about dark matter and dark energy. So I made this comment, and yeah, I'd planned it in advance. I think it's great. But anyway, so that takes me, oh, there's a picture of me at the Nobel Ball that I was telling you about. When, yes, I had to go to the restroom. But anyway, so I want to end up with this picture, which is my book, The Cosmic Cocktail, and it's on Amazon. I think it's like $10 or something. So if we were in the real world, I would have copies for you, but you'll have to just go on Amazon and look for it. And I want to just comment on the Cosmic Cocktail recipe, which out of in a 10-ounce drink, you'd have to have, well, let's look. I wanted to say again, only a millionth of an ounce supermassive black holes. They don't play a big role. Neutrinos at 5/100ths of an ounce, stars and ordinary stuff, up to half an ounce. And then, but the bulk of it is, well, I guess more like 2.5 ounces of dark matter and 7 ounces of dark energy. And then in the early universe, all these things were bumping into each other all the time. So I would say shaken and not stirred. So that's kind of my recipe for the universe. And I think I'll stop there.
Thank you very, very much, Katherine. This is a wonderful, stimulating, and entertaining presentation that you've given us. And at this time, we'd like to take some questions. So some folks have already figured this out. If you enter your question in the Q&A, we'll pick it up and we'll pass it along to the speaker. And we will try to get to you. So assisting with the Q&A and very much appreciated is Professor Francesca Ferrer. And so Francesca, I'll ask you to help sift through the questions. And
yes, we already have a few of them. So maybe I can start with the first one. Kate was confused. She finds a bit counterintuitive for something to expand while cooling. She's thinking like the bread with the raisin was expanding due to heat.
It's so funny. Now I'm going to try to think of ordinary real world examples. That's always the hardest thing, isn't it? So, so heat means that a temperature or a heat means that things are moving really, really rapidly. And so as the temperature cools down, they're moving less rapidly, which is why they're not bumping into each other as much. So if you have air and you cool it off and you in equilibrium, it's going to expand. You just let it go. I don't know if that's a satisfactory answer or not, but
I think it makes it clear that there is more going on in the pie than what it looks like. Moving on, Scott is asking whether there is a credible competing theory that contradicts the existence of dark matter and dark energy.
Okay, so on the subject of dark matter, there's been a long discussion about one could explain rotation curves in a theory called MOND, modified Newtonian dynamics. So in this case, that would mean that we would abandon Newton's laws. And instead of the ordinary F equals ma, then as you go out to the farthest reaches of the galaxy, the acceleration is really low out there, things are moving more slowly out there, then that the Newton's laws would be different. And so that is what would be causing the rotation curves. And in fact, you can write down, if you just make a postulate that Newton's laws change, yeah, you could get the flat rotation curves. But the problem is at this point, we have all these other pieces of data that are a lot harder to match with this kind of theory. So you know what the real killer is? It's actually the cosmic microwave background. So we can really see the difference in the behavior of ordinary matter and dark matter, and otherwise you wouldn't have the peaks the way they are, and we can study those hot spots and cold spots. It's really difficult to make that work with this modified Newtonian dynamics. And nowadays the original MOND model has gotten more complicated. There's one called TEVIS, where in addition to you need a bunch of new types of fields in the model, and you need dark matter as well. So I think pretty much everybody agrees there has to be some dark matter. And what about the bullet cluster? How are you going to explain that you have the gas getting stuck, the dark matter moving through? And so if you put all these different pieces of the puzzle together, it becomes really hard to avoid dark matter. So at this point, I would say, no, there's no competing theory for dark matter. Dark energy, oh yeah, we have no idea what's going on. So is it possible that Einstein's equations need modification? Well, people have tried that, and the attempts have not been too successful so far. It doesn't mean it's not going to happen. So dark energy, oh yeah, I'll give you that one. Please be some brilliant young person come out and tell us what's wrong with that picture, because it's very, very bizarre. And I can see Francesca smiling, because I know you agree.
Yeah, I hope that Scott is working on that already. But Pavel is asking something about inflation. He points out that at the end of inflationary period, there have been estimates for the size of the universe. And these estimates range from a meter to many light years across. So why there is such big variation in estimates? Is there an accurate number? Does this take into account already the presence of dark matter? How large is the universe at the end of inflation? Can we say it? Do we know?
So I don't think we talk about the size of the universe after inflation, actually. I do think that what's possible is that different patches of the universe inflate more or less. So maybe that's what is that what you're talking about? I think you're talking about a multiverse. So there was a period of exponential expansion in the early universe, but some regions could have expanded for longer periods of time than other patches. And so obviously we know how much our patch has expanded, at least a minimum amount that our patch has expanded, because there's something called the observable universe. We can only see out to the age of the universe times the speed of light. So the 14 billion light years, that's as far out as we can see, because anything farther away than that, it would take longer than the age of the universe for the information to get to us. So it's possible that once you go out beyond there, well, maybe there was some patch of the universe that inflated more, inflated less. And so you could have a bunch of it's the multiverse, multi-universes out there, essentially, of different sizes. So maybe that's what you're talking about. I am not a fan of the multiverse. I don't think it's required. And I think that I prefer at this point, it's philosophy, because if we can't probe outside the observable universe, what are we talking about?
Yeah, probably they don't have cocktails in these other universes. So we stick to our universe. And Kenneth is asking, why is ordinary energy missing from your pie chart? We have dark energy, but where is ordinary energy?
Oh, that's all part of the 5%. So I should have clarified that. So ordinary matter, ordinary energy, they can convert into each other. And so when I should say ordinary stuff, that's included in the 5%. Absolutely.
Eric asks you if you can elaborate a bit more on the use of DNA to detect WIMPs.
Sure. So I had this picture of these hanging strands of DNA. And the idea is that in one of these strands, I could control exactly what that strand looks like. So the different bases of DNA of A, G, C, T. So I would set it up so I know exactly what it looks like, so that when the gold comes through, if it breaks the DNA and that falls down, I can go, aha, the broken piece. I know where it was. And I know it was right after the G and before the C. So I know where the break was. So that's how I can figure out where the track is. And the amazing thing is the distance between the bases is like some nanometers. So we're talking nanoscale tracking. It's nano being 10 to the minus 9 meters. So it's, wait, is this meters or centimeters? Meters, right?
Meters.
Thank you. Anyway, so if you could actually figure out where the track was in that direction with that kind of accuracy, that's pretty cool.
Mm-hmm.
So the current status of this is that we've got the world's best biologists involved, people like George Church and Charles Cantor. And they were the ones, when I was shocked to learn, they were, oh yeah, piece of cake, easy. The biology is easy. You can make with polymerase chain reaction, you make 1 billion copies of the broken strands, and of course you can set it up, and of course you can figure out where the break is. I was like, oh. But the problem is that, in fact, George Church set it up. He's got somebody put it in a centrifuge to straighten out the DNA, and he put it, and it's now in his freezer waiting for the physicist to come along, who's going to take care of the radioactive problems that we can't use gold, is too expensive, but whatever element you're going to use, you have to make it really not be radioactive, because then you would have all this junk coming out of it. So that's the hard part, and we haven't gotten the physicists on board.
Mm-hmm. And just to reassure, Elliot was a bit concerned. Are you suggesting that WIMPs or dark matter could cause genetic mutations?
Oh, I see. No. The WIMPs do not break the DNA. No problem at all. WIMPs go, as I said, there's billions going through your body. One hits one of your nuclei maybe every few weeks. It depends on the details. And they do nothing to you, completely harmless. Okay, so we actually wrote a paper on that because a journalist asked us that question. So the cosmic, I don't know if you've heard of cosmic rays. So out there's tons of particles flying around in the galaxy, protons, and when the protons hit the atmosphere of the Earth, they turn into other particles. And so we are being struck all the time. And these are particles that have electric charge. They are damaging to us. So you could be getting cancer because you're getting hit by cosmic rays. And if you go on an airplane, yeah, if you're going on the wrong day and there's a huge cosmic ray count because the sun had a solar flare, yeah, you could die. I'm serious. The cosmic rays are very serious. And that's why it's very hard for astronauts to go to Mars. One of the main problems, other than having your eyes destroyed, which is the other big problem. And one of the big problems is the radiation. You can't tolerate that kind of radiation for too long. I met a bunch of astronauts, and the Association of Space Explorers came to Sweden, 109 astronauts. Oh, that was fabulous. And I met the guy who'd been up there the longest on the space station, an entire year, an American guy. Now he's been beat out by a woman. But anyway, so up there in a year, because the farther away you get above the atmosphere of the Earth, the more dangerous it is from those cosmic rays. Anyhow, so WIMPs ain't nothing. Now, what the WIMPs do in this detector is they knock the gold forward. The gold can break the DNA. So if you're being bombarded by gold atoms, that's not good, but I don't think that's going to happen. It might be good if you can collect the gold. I don't know.
Very good. And then there are, let me combine two questions from two different Johns. The first John is asking, can you explain a bit more why there is no center to the universe? And then dark matter, is it only in galaxies? Is it everywhere? Can you explain a bit more where it is? Is it also in interstellar space? So why there is no center, and where is the dark matter?
Okay, those are two different questions. So I'll start with the second one first. So dark matter started out everywhere, pretty much uniformly distributed. But, and here's where inflationary cosmology comes in. There were some regions had just a tiny amount more. So this, let's say this region of space has a little bit more dark matter in it, then this region has a little bit less dark matter in it. Okay, and we're again 1 part in 10 to the 5, really tiny differences. But the part that had more matter in it had more gravity, so it collected more and more stuff. And so it collected more and more and more and more, and eventually this region that started out with this tiny overdensity above the average would end up being a galaxy. And this region that had a tiny underdensity relative to the average, this thing ends up being a void. So dark matter on the average, it started out being pretty much everywhere, but then it clumped together to make galaxies and clusters and all that stuff. So now it's not uniformly spread out anymore, no. So that's the answer to the second question. Now, if I can remember what the first, what was it? Oh yeah, the center of the universe. Okay, so let's go back to 1915, Einstein's relativity. Then people had to put their thinking caps on, and they made some postulates. They said, what if the universe is homogeneous? In other words, it's on the average, it's the same everywhere. There's no preferred point anywhere. They made that assumption. They made that postulate. They made a second postulate. There's no preferred direction. No matter what direction you look at, it should always look the same. So, and those two symmetries can be written mathematically more accurately. But with those two postulates, you can then take Einstein's equations and say, with these, if you make these assumptions, what equations do you get? And those are the equations we now call the Friedmann equation. And those are the equations that you use to do the evolution, to study the evolution of the universe. And, they were just making this stuff up. That's the cool thing about science. It's just guesswork. And they died without realizing that they completely nailed it. They're completely correct. Every prediction, that if you start with those equations and you move forward with matter and radiation and da-da-da in it, then you get our universe today, and everything matches, works to exquisite detail. So this assumption, at least the part of the universe that we can see, appears absolutely to be correct. So it was a guess. And at this point, we can do more than just say, well, the mathematics leads to a universe that works. We also have data. So we have Sloan Digital Sky Survey, you have the bunch of different galaxy surveys on very, very large scales, and you can look around the universe and you can prove with statistical analysis of the galaxies that on the average, it is homogeneous. And so there's no particular favorite place. Oh yeah, now there's one caveat. Some people say, well, instead of dark energy, what if we're sitting in a weird underdense place in the universe? Okay, so that possibility still exists, and which would violate what I just said about homogeneity in a very, to a small degree, but so that is still possible. Would you agree, Francesca?
I agree, although it would be very special.
Yeah, yeah. So I shouldn't be throwing in these bizarre caveats that probably don't hold, okay?
No,
But you
but
know how
it's
scientists are.
important, is it? Yes, yes. And
Scientists always have to point out the one possible mistake in their reasoning, and then puts like with the vaccine, it could do this and that, when they should have just said, damn it, it
Yeah.
works, take it.
no stone left unturned. The audience is fascinated by your proposal of dark stars. So there are a few
Good, me
questions.
too.
Yeah, yes. So then now, since we have you here, we want to learn from the inventor. Elena is asking you to clarify, well, bright stars run on nuclear fusion. When the fusion matter runs out, the star explodes. Would the dark stars operate in the same way? Would they explode at the end, or do they actually condense? That's the first question. And maybe while you're at it, there are two questions that are related. How could we tell the difference? Is there an observable? And if the dark stars formed in the early universe, why are they not forming now?
Oh boy, this is so many questions. I'm
Hey,
not going to
people
remember
digged
them all.
into it. Yeah.
Well, okay, so let me start with explaining why they existed in the early universe and not anymore. So they had to exist at the right place at the right time. So in the early universe, you've seen these pictures I showed of halos of galaxies. Well, let's talk about our galaxy. So the sun is not at the center of our galaxy. So the amount of dark matter is, there's more dark matter at the center of the galaxy than there is farther out. So where we are in our galaxy, there is not enough dark matter to power the sun. Okay, it's just the amount of dark matter isn't enough. There's enough dark matter, you can capture some of it and look for signals of it and blah, 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 but it's not enough to be a power source. These first stars, they formed smack in the middle of these protogalactic halos. So if right in the middle, that's where there's tons of dark matter. So they were in the right location. And there's some other reasons as well, but I guess I would say that's the main one. So so you have to have really, really a lot of dark matter around. That's the bottom line. And so the early stars were in the right place to have that. But then eventually, and then they would collect more matter and get bigger and bigger. And then this initial small protogalaxy would merge with other protogalaxies. And eventually they wouldn't be in a region where there's a ton of dark matter anymore. And then they would have to start to collapse because there's not enough, the pressure source from the dark matter annihilation wouldn't be there. So these stars would start to collapse. And you're asking what would happen. Well, let me just say that not all stars explode as supernovae. That's only certain types of stars that do that, okay? And in fact, these guys would not do that. So what they would do instead is they might have a brief fusion phase if they're small enough, but they should collapse to black holes and they would not explode. And that's one way you could tell the difference. So a star, if you see stars, a population of stars that's exploding, well, that's not us. But another major way to tell the difference, if you're looking in the very early universe, well, people don't really know. The standard stars people are talking about is the first stars are really small and would not be bright enough. You couldn't see them at all. So if you have a standard star that is powered by fusion, it's hot. So it can't grow very large because it blows stuff off because it's too hot. So we are predicting really bright objects, and yet they're really cool. And you can tell what the temperatures of stars, you can tell by what color they are. So this thing looks like the sun in terms of color. So you should be able to tell the difference between this and other things.
And Chris was a bit confused about something that you said. Dark energy, you mentioned, is 70% of the contents of the universe, but it doesn't feel gravity. Is it 70% of the mass? What does this 70% mean? 70% of what?
Okay, so the energy density of the universe is when you add up all these different pieces. And that is the number that we know that corresponds to the flat geometry, the 10 to the minus 29 gram per cubic centimeter. So these different pieces, you have the ordinary matter, the dark matter, all three of them have an energy density associated with them, which is a positive quantity. The dark energy might have a negative pressure, but it has a positive energy density. And let me again say that the one candidate that people talk about the most is it would be a vacuum energy density. Okay, so the vacuum where particle antiparticle pairs pop into existence and then disappear again. They last only 10 to the minus 43 seconds. So this is a vacuum that we know exists. It's been measured. You can test it. But we don't know if that's what the dark energy is made of. Whatever it is something that has a positive energy density and contributes 70% of the total energy density.
Yeah, and going into the same thing, the relation between different dark components. Could dark energy transform into dark matter? And
yeah, that's a good question. So first of all, regular matter and regular energy do, yes. However, dark matter and dark energy are terrible names because they give the impression that they would do the same thing, but they probably don't. Okay, so the only thing they have in common is the word dark. They're not giving off light. It's a crappy name, even though my friend Michael Turner invented the name dark energy. He'd kill me, but I think it's a bad name. Anyway.
Tell him. And is there a theory or an explanation for why there is the relation between how much observable matter compared to dark matter?
Oh, yeah, that's a weird thing. There's 5 times as much dark matter as observable, which leads people to wonder, so there's something called asymmetric dark matter. And so for example, what if the simplest example, what if you had, I'm going to back up. What if you had equal numbers of particles and one of them weighed 5 times as much as the other? Okay, so then you'd have the energy density in dark matter be 5 times as much as normal matter, just because it weighs 5 times as much. So people are playing around with models like that. Yeah.
Now a question related to an experiment. Bill McKinnon at Earth and Planetary Sciences points out that GWST is launching this year, so let's hope it's lucky.
No, it was supposed to. Of course, it's been delayed because of COVID. I mean, it's always going to be next year for eternity, I think.
Let's hope it happens, because Sean is asking what makes it so particular. Why is it such a promising tool to see dark stars? Is there light? Is because the light is going to be redshifted, and then is that the?
So the basic thing about the James Webb Space Telescope is it can see farther out, which means farther back in time than the Hubble Space Telescope. So the Hubble Space Telescope goes to about a redshift of 10, and the James Webb is going to go out farther than that, farther back in time. It sees not only visible light, but also infrared light. So things that emitted in the visible light back early on, that light would have been, the wavelength would have been stretched, would have been redshifted. And so you need an infrared telescope to see that. So it's a slightly different wavelengths that it looks at. So it allows you to go farther back in time.
And Craig is wondering, how fast do WIMPs travel?
Well, inside the galaxy, it's controlled by the gravitational potential of the galaxy. So the amount of mass of the galaxy determines its speed. So inside the Milky Way, it's about 300 kilometers per second. So wherever it is, it depends on its location, but that's the answer inside our galaxy.
And John is asking, do we expect dark matter to be related to dark energy through the famous Einstein's equation E equals mc squared?
Oh, that's the same question I answered before about the relation between mass and energy, and no.
No, the answer is no.
Yeah, the answer is no.
And Joao is wondering whether ordinary particles can eventually decay into dark matter.
Well, that's a good question. People definitely play around with theories where dark matter can turn into ordinary matter, or the other way around. So the answer is maybe. Very good thinking. So the dark matter, for example, instead of a regular photon, could be a hidden photon, and they interact with each other and kind of indirectly, I guess. So yes, these are very interesting models.
And yeah, moving on to the theory space, Kristen is asking whether higher dimensions are real and whether they would have a relation with dark matter and dark energy. And along the same lines, whether string theory provides an explanation for dark matter and dark energy. That's another question that's been asked in the.
Well, the reason these questions are related is because for string theory to work, you have to have extra dimensions. So in addition to the three, well, we know we have one time dimension and we have three space dimensions, that up, down, left, right, forward, back. But for string theory to work, there have to be 10 spatial dimensions. And it depends on the model, but typically they might be very small. So it's like on the weave of a carpet. You don't even know it's there until you go look really closely. But the problem is that we as human beings, we are too big. So we can't get into the weave of the carpet. So we don't even, we can't be sure if it's there or not. But so that's kind of the idea of of the typical idea of extra dimensions, but it is certainly possible that they play a role in the dark matter and the dark energy. There's no doubt about it. So, yes, there could be yes, there's so many different ways it could be. So I don't even know where to begin, but yes.
And now finally, probably moving on to voids. You mentioned voids in an answer to an earlier question. Is that the absence of, so when you mention void, do you mean that the absence of any matter? Can matter go through a void, or is it like a bubble?
Okay, so a void does not mean completely has nothing in it. It means it's about a fifth of the ordinary density or something. So it's lower density than its neighborhood, but it's not completely empty or anything like that. So yeah, it's just lower density. So some regions become galaxies, and some which have more density, and the other regions end up lower density, but they're still not completely empty. No.
Mm-hmm. And there's been a couple of questions of where would WIMPs fit in the standard model? Do we have? Would there be?
They're not. So the standard model is now completely understood. We've seen everything in it, including the last thing was the Higgs boson. And yet it does not explain the dark matter. It does not explain a lot of things. And so the dark matter by definition has to be what we call beyond the standard model physics. And WIMPs are definitely beyond the standard model physics. And an example I gave you was supersymmetry. So in supersymmetry, you would have all the standard model particles. All of those would have partners that are not part of the standard model. So yeah, that's the problem. We have to do something completely radically new because dark matter is not in the standard model.
Then also, is there dark matter in or on the Earth?
Oh yes, yes. Oh yeah, it's everywhere, including here, including in this room, including racing through your body.
So I think there are.
Well, I think, what is it? Oh, help me remember those numbers. They're like at any one time, there's one per coffee cup or something like that. Is that right?
One per coffee cup. So,
I think that's right.
That's right? Because
and they're not sitting in the coffee cup. They're racing.
They're moving. They're racing at 200.
On the average, there's one at any given instant. There's one in a coffee cup. Yeah.
It's surprising that we don't feel them, but they are here.
Yeah.
So that was great. There are a few more questions, but I think I don't know if Brad can.
I think we're probably coming to the close of the Q&A, and I certainly thank everybody for these wonderful questions. And I think it's probably time. Katherine is an hour later than us, and so we probably should let her go pretty soon. But before
that is true. I have to say this has been a lot of fun. You're all keeping me awake. That's for sure. So thank you for all being here.
Yeah, so I'd like to again thank Professor Freese for a marvelous, stimulating, and most entertaining lecture on what really is one of the great, outstanding scientific issues of our time. And I'd like to add that if you enjoyed her lecture, you will most certainly enjoy reading her book, The Cosmic Cocktail. And I'll try to hold it here to my camera so you can see it. But you've seen pictures before. In this book, just as in her talk, she brings the science to life. She puts names and faces of many great scientists who have participated in this quest to understand what really makes up our cosmos. And she does this in a wonderfully engaging and approachable way. And with that, I would just like to thank you again, Professor Freese, and thanks to all of you who joined us tonight, and say good night.
So I want to thank Brad and Francesca and Mark and everybody else involved in making this happen. So thank you so much.
We're so pleased that you could be with us, and we look forward to the time when you can be here in person.
Sounds great.
Thank you.
So,
Good night.
thanks everybody very much. Thank you, Francesca, and apologies to the questioners who, if we didn't get to some, I know we probably didn't get to them all, but it's a wonderful group. So thanks again to all. Okay. Well, I think we will go ahead and bring this to a close. So Simone, if you're ready, I think you could go ahead and we'll say goodnight, Katie. And thank you again. Wonderful. Take care.
Good night. Thank you.